Outreach programs into rural communities are essential to both the mission of OHSU and to the care of those folks that reside in the Oregon area.
I'm in Astoria today for the KCI Institute van that's here helping people all over Clatsop County.
These programs will provide care to people who may not otherwise be able to afford or have access to that same high level of care that OHSU is able to provide them.
The On-Track OHSU program works with students in 6th through 12th grade who are traditionally underrepresented in the sciences.
We have mentors from OHSU that come and work with our students so that they can get a better understanding of what they could do once they leave Jefferson High School.
Night for Networking is the largest networking event for people with disabilities in the country.
What Night for Networking hopes to accomplish is to be able to give people with disabilities an opportunity for employment.
It means that there's hope in the community for me to reach my potential and other people to reach their potential, even though they have a disability.
Virginia Garcia has a rich history of collaborating with OHSU and having the students come and be exposed to community dentistry.
I think it's important to have dental students here at Virginia Garcia treating our patients. It helps them get more experience and see different types of patients than they see at the dental school.
I feel like that we're doing a great service here, providing dental care for underprivileged people at a lower rate. And if this clinic wasn't here, a lot of people would just neglect their dental health.
OHSU really understands the importance of primary care and community health and improving our population's health. And OHSU collaborates with partners across the state to improve the health of Oregonians, where people live, work, and play.
The torchbearer. It's not a job you apply for. It's not a position you're voted into. The torchbearer is a calling. Answer it, and you'll forever see the world not for what it is, but for what it could become.
It's my pleasure to welcome you here to the second of our 2016 Brain Awareness Season lectures. We had a wonderful turnout last week for Dr. Kathy Grant's lecture on alcohol in the brain, and I hope that some of you will join us next week as we delve into marijuana in the brain. For those of you who were here last week and in previous years, I apologize for the repetition of these announcements, but I'll try to be brief about them. First off, please take a moment to fill out the feedback form, that's this large form here, that you received with your program. We value your opinions, and your feedback helps us to improve these events. At about 7:45, the ushers will be coming up and down the aisles, holding up smaller pieces of paper. Please write your questions on these and hand them down the aisle. We have a few physicians present who are volunteers who will sort them into areas of interest. Please write clearly for them. We've upped the lights a little bit this evening, so you should be able to see. After the lecture, please join us for an informational reception in the lobby following Dr. Gazzaley's lecture. The Friends Group of OBI BrainNet, or the Brain Research and Information Network, will be selling chocolate brains and books. We're also delighted to have Dr. Joel Nigg as our expert at the Ask the Expert table. Dr. Nigg, who has lectured at Brain Awareness before, is a professor of psychiatry, pediatrics, and behavioral neuroscience. His research focuses on the underlying mechanisms and causes of ADHD across the lifespan. Finally, I'd like to point out that one of the realities of scientific research is that we need you to partner with us to produce healthcare breakthroughs. Many of you in the audience provide substantial philanthropic support to OHSU, and we want to thank you for that. I hope this lecture will inspire you to think about supporting medical research. Research is improving human health right now, and you'll see how research can change the lives of patients through what our speaker has to say tonight. Your philanthropy is part of what makes this possible. For example, Dr. Nigg's work on ADHD, in addition to his NIH funding, is supported by significant philanthropic contributions. And now I am delighted to be able to introduce tonight's lecturer and distinguished scientist, Dr. Adam Gazzaley, Professor of Neurology, Physiology, and Director of the Neuroscience Imaging Center at UCSF. Dr. Gazzaley was born and raised in New York City. He was awarded his medical degree and a PhD in neuroscience at the Mount Sinai School of Medicine in New York. He completed residency training in neurology at the University of Pennsylvania and postdoctoral training in cognitive neuroscience at UC Berkeley. Dr. Gazzaley's laboratory studies of neural mechanisms of perception, attention, and memory with an emphasis on the impact of distraction and multitasking on these abilities. His research approach utilizes a combination of various neurophysiological tools, including functional magnetic resonance imaging, electroencephalography, and transcranial magnetic and direct electrical stimulation. His most recent studies explore neuroplasticity and methods to optimize cognitive abilities with custom-designed video games. Dr. Gazzaley is also the co-founder and chief scientific advisor of Achille Interactive Labs, a company developing therapeutic video games. He is a stimulating lecturer, and I am certain that we will all leave tonight's lecture with new ideas and perspectives on future possibilities for enhancing the human mind. Please welcome Dr. Adam Gazzaley.
Hello, everyone. Thanks for coming out tonight. I'm looking forward to sharing with you this evening some perspectives on a future, a vision of what we might accomplish in neurology and psychiatry to better our lives. I want to start by talking about performance, in particular high-level performance. And I would say that it's clear that us modern humans have really always been consumed with high-level performance. And when it comes to this world, the world of physical fitness, it's really been the pursuit of optimal performance that has been this growing global obsession for many decades. So if you think about strength, endurance, power, speed, flexibility, balance, coordination, across every one of these domains, you can find specialized programs, equipment, and practitioners, all devoted to optimizing the performance in physical fitness. Which really begs the question, what about the human brain? What are we doing to optimize those core abilities of the brain that really most define us as human? Our perception, our memory, our emotional regulation, our decision-making, even things like compassion and wisdom. Unfortunately, I would say in this pursuit, we've really been tragically lacking. So if you think about improving cognitive abilities of young, developing minds, that would fall into the purview of the education system. But we've seen there a real focus on the transfer of information content, but not building the underlying information processing systems that depends on. If you think about cognition in healthy people, then it falls into the category of wellness, where it's really largely been marginalized as alternative. And how about boosting cognition in those individuals that are suffering from deficits? Now we're in the world of psychiatry and neurology, where we've had this incredibly siloed approach of using small molecules, also known as pharmaceuticals, and not really branching more broadly than that. And I feel like we've really paid a price for that siloed focus. So before we move on and talk about the future, let's pause and go through our current approach and dissect a little bit more out where I think the deficits exist right now, and do it from both the perspective of medicine and education. So our goal here is to improve cognition and how we're thinking. And this is broad, right, including things like emotional regulation and mood I'd put into that category. So the first problem is that we have very poor assessments. Now, we have great assessments in the laboratory. We do functional brain imaging and all this very sophisticated technology that we bring to bear in understanding how the brain is functioning. But in the real-world setting, in the clinic or the classroom, these techniques have not really crossed over. So if someone goes into a doctor's office, or you look thinking about a child in a class, we don't really actually know how their brain is functioning that might be accounting for challenges that they're having. And so that's one problem, is that we have a very low understanding of what's happening in each of our brains that might impact our lives at any given time. But that doesn't prevent us from treating, as I'm sure you're aware of, right? We don't even have to know what's going on to give someone one of these, a pill. And I'll just talk about medicine for the first part and then create the analogy for the classroom. We have this approach that's by far the dominant way of treating psychiatric and neurological disease for the goal of enhancing cognition. Now, there's nothing inherently wrong about using a small molecule to improve cognition, but we've been trying for 50 years to do this, and we really have no major win. And that's because these are just generally very poorly targeted. They act on neurotransmitter systems, which are very distributed across the brain and not targeted to the underlying computational unit of our brain, which is the neural network. Therefore, we have to increase our doses to very high levels to get the effects we want. And what we wind up with are really just as many side effects as effects. That is the reality. We have this very sort of blunt approach to treating. Classroom, similarly, would not, because we have these poor assessments, we're not actually targeting our approach to building the strength of young minds necessarily, just really trying to transfer the content and then collect how much of that has really endured. The other problem is that both systems are very non-personalized. So our medical system, the prescriptive advice that we give is really based on large population studies that don't account for all the individual variability and heterogeneity in those populations. So despite the fact that they're poorly targeted, on top of that, they're also not really targeting the individual and that person's brain. Same thing could be said for education. Curriculum is also based on population data, not on individuals. And then they're often unimodal, another way of saying siloed, focusing on one type of treatment. Many physicians, the better ones don't, but many do think of drugs, even one particular drug, sort of as a holy grail. And I just would say for something as complex as the human brain and the mind, that we are unlikely going to have a single solution to improving our cognitive abilities. It's most likely going to be a multimodal approach. Same with education. The classroom's not the only place that we're going to succeed in improving young minds. And then what might be the biggest problem is that these are open loop systems. Now I'm going to come back and talk about closed loop, the opposite of that, in great detail. But in just a quick snippet on this, open loop is where you have a very poor cycle of intervening in some way, updating that intervention, and then reapplying it again. And so that is another problem with both these systems. And as I said, I'll dive into that in more detail. So I would say that this is just not good enough, right? 2016, that our two main giant institutions to improve the function of our brain, to have all of these very fundamental deficits is something that we need to correct. And so what we've been working on in our lab for really over a decade now is developing a new approach, one that's targeted, personalized, multimodal, and closed loop. And that's basically the theme of this talk. I'm going to take you through the ideas behind how we might do this, show you some data from our lab of our first attempts to accomplish it, and then stretch 5, maybe even 10 years into the future when we can actually see an example of how this might work, how we might have this approach incorporated into our daily lives. How might we do this? Well, one possibility is technology, right? So we see technology everywhere and its power, and we know that we're living in extraordinary times, right? The explosion over the last decades in the accessibility and diversity of information technology has been, profound. And right now, we're really standing at the verge of a phase shift as a whole new layer of technology is emerging into the marketplace. So from consumer level virtual reality, augmented reality, wearable physiological devices, motion capture, artificial intelligence. So I'm not going to spend a lot of time on this. If you're not familiar with all these, you will certainly be in the next couple of years as we start seeing these land in our homes. Most of these are really designed for entertainment, media, and communication. The question that we've been asking in our lab is, can we take this technology and use it as tools to enhance our cognitive abilities, to elevate our minds, and really refine our behavior? That's the goal. Can we leverage off of all of this amazing innovative development to create those types of tools. Now, some of you might be asking yourself, how's that even possible? These are really largely superficial in how we interact with them. How could they produce something, a result as meaningful as what I just described? And it's really not all that complicated. It comes down to the fact that this technology can be used to create very powerful experiences. And experiences are the gateway to brain plasticity, right? That wondrously complex dance of change that occurs in all of our brains all the time at every level, from its function, its structure, and its chemistry, constantly rechanging itself. We know that the relationship between experience and brain plasticity is a very powerful one, right? Even witnessing a single tragic event can produce damage to your brain that detrimentally affects the rest of your life, right? We call that PTSD. And so the challenge that we're looking at is to harness brain plasticity by creating experiences that improve how our brains function. That's the basic idea, right? How can we build those powerful experiences to allow our brains to develop and change in a way that enhances our cognition? We do that really through the creation of closed-loop systems. So now let me dive in deeper to this. A closed loop works like this. You intervene in some way, and there are both physical and biological examples of closed loops. And you record the impact of that intervention with as low latency as possible. That means as short a time, you record what happened. Based on that data, you reformulate your intervention and apply it again. Record, update, apply. Every cycle refining and optimizing that intervention in a personalized way to what you're trying to impact. This is undoubtedly the most powerful way to change any system, again, physical or biological. And so if we could develop closed-loop systems, we should be able to change the brain in a much more effective way than our current system, right? Think about the open-loop system of medicine right now. We give a drug with all of the deficits that I described. Someone goes home, months pass sometimes, where the patient subjectively records their effects and side effects, comes back to the clinic, and then gets a really non-evidence-based decision to go up or down a little bit, right? The art of medicine. And I'd say that's not really refined enough for what we need to do. We need a closed-loop system. Same thing with the classroom. Long periods of time exist between when a lesson is taught, when a test is given, and then the updating is not even cycling back to that person. So, closed-loop systems. How would we create them to improve brain function? What type of technology would we use? I would say that in our hands and from the perspective of our laboratory, the perfect form of technology to create a closed-loop system are video games. Now, some of you might be asking yourself the question that many people do. But video games are just another manifestation of human mania, our endearing quality of going relentlessly after absolutely pointless goals. How can this be a tool to help the functioning of our brains? This is from Time Magazine, 1982. And I could tell you that the world of video games have changed dramatically since then. There's an entire field, it goes by different names. I think of it as games for impact. It's using the mechanics and engine of a video game to have behavioral change as the outcome, not just entertainment. And I could spend an entire hour showing you examples of that from around the world across many different domains, but I just want to focus on one example. This is a picture of a game known as a first-person shooter game. Arguably the most controversial of all video games because they have the highest violent content. But if you haven't seen these games, I really urge you to at least see one being played so you could be aware of what's going on. I mean, this game is completely immersive. It's like watching a major motion picture, except you're a character in it looking out through your own eyes. And what's going on in this game is an intense interaction over time, usually in a very highly charged, emotionally charged setting, like a war theater, thus the violence. But very rapid decisions are made that require great selectivity, and then you have to move your attention, hold information in mind, basically challenging your brain in a very fundamental way. And research shows that the young people that play these games, when you compare their cognitive abilities on laboratory tests to their peers that don't play these games, you see that they have much higher, superior abilities. And if you take young people that don't play these games and have them play it for 10 hours, compared to another group that plays a game like Tetris that doesn't challenge the brain quite in this way, you start seeing those same improvements in what we call cognitive control abilities, our attention, our working memory, our ability to task switch. And I was very interested in this data. We did not do any of these studies. But with our goal to build these closed loops, I started thinking about video games and how that might work, and then how we might be able to bring in all this other amazing technology that is just being developed right now into the closed loop. So what I'm going to do now is I'm just going to sort of tell you the end of the story before we get there, and then I'm going to back up and break it down again. But this is essentially how we think about using video games in this way. So here you are, your brain playing a video game. While the game is going on, events are taking place in your brain, and that guides your performance. How fast you are, how accurate you are. The game can record all of that data in real time. It knows exactly how you're performing. And then it can feed back to you a scaled environment that's appropriate to how you're performing. So it's challenging you right at that level. And we think about this closed loop in two ways. One, the game could give you a difficulty level in real time that's adjusted to your performance. So no matter who plays it, whether you're 70 or 75, the game will figure out where your sweet spot is and then hold you right at that level. And as the plasticity mechanisms of your brain advance your abilities over time, the game just baby steps, like a personal trainer, every single second, just pushing the system ever gently into a higher state of performance. The other thing we could do in real time is give you feedback so that you know how you're doing, so that you could learn over time. So this is really the core of everything that we do in our lab, is creating these very dynamic closed loop systems between your brain and video games. We call that the video game engine. The other thing we could do now is take new technologies like motion capture and physiological devices. Many people wear them right now, just usually to quantify their physiology and their behaviors, but not really in an actionable way. But we could also feed that data into the video games so that the game can understand you in a much deeper way. And then we could present richer, more real-world, immersive environments like virtual reality and augmented reality, which is an overlay on the real world. This creates much more engagement in the entire process, this whole closed-loop system. And then we could wrap all this together with artificial intelligence algorithms that could really handle this bidirectional flow of data. So what we wind up with here is a truly integrated, multimodal closed-loop system. And I think that the future will show us that this is the most powerful way to improve brain function and really shape it in a certain direction. So let's make that less abstract now. Let's talk about some examples. So if we head back in time 8 years ago, I asked myself this question and my lab. Could we build a video game, a custom-designed video game, not pulling one off the shelves that has all the violent content, which has its own degree of complications, and design that game to improve cognitive abilities, what we call cognitive control, in older adults? And the reason why I picked this area to focus as the first domain was because we've learned in our own lab that these abilities, which I mentioned, attention, directing your resources, your limited resources in space and time where you want them based on your goals, holding that information in mind, working memory for short periods of time, and then moving fluidly between multiple goals, what we call task switching or multitasking. All of these abilities decline with aging, independent of things like Alzheimer's disease. And we've shown this in our lab for many years using those tools that you heard about, that what we use to understand the brain. And so I had the hypothesis based on our work, because what we've shown here is that these abilities are related to each other mechanistically by similar networks in the brain. And so the hypothesis was that if we created a closed-loop video game to put pressure on one of these abilities, like multitasking, which is a form of goal management, that we would see a benefit in other forms of cognition that used similar mechanisms. That was the question we set out to ask. In order to do that, we built a video game. This is what it looked like. It's called Neuroracer. I reached out to friends of mine that work at George Lucas's video game company, LucasArts, and I said, I have an idea for a design of a game in mind, but I work in a neuroscience lab, right? We don't have the expertise to build a game, especially a game as complicated in terms of the closed-loop engine that we wanted to create. So My friends donated their time. These are very high-level video game developers building Star Wars games for many years. They came down to the lab and we created Neuroracer. Let me show you what it looks like. On the surface, it's a simple game, but what's going on under the hood is really a bit more complicated, and I'll come back to that afterwards. This is how you play Neuroracer. You play with a joystick. You're driving a car on a road, a three-dimensional road. You're trying to maintain it left, right, up, or down to keep your position right in the middle. And then at the same time, you're responding as rapidly and accurately to target signs like that green circle. Not red circles, not green pentagons like this, which are very hard not to press to. And what's happening here is that these two tasks, the spatial navigation task and this perceptual discrimination task, what we call the driving and the sign task, are both on independent adaptive algorithms. What that means is that as you get better at each of them, they get harder. The amount of time that you have to respond to the sign gets shorter and shorter by milliseconds as you get better at it. The speed of the road increases as you manage to maintain yourself in the middle. But they're both incredibly attentionally demanding tasks, and they always maintain that degree of need of focus because they're constantly pushing you at your ability. You never get perfect at it, ever. Now, if you're going to play this game, one thing we've learned is that you, whether you're conscious of it or not, would trade off between these two tasks. It's very hard to do them both at a high level at the same time. So you'd focus on the driving task and miss signs, or vice versa. So what we did to avoid that, because what we wanted our participants to do was to try to do them both at the same time, to try to get better at that. And so we simply tethered across these two tasks with the reward cycle. And what we found is that everyone, including 80-year-olds, want to level up on video games. It's some inherent natural part of just being a human. And so that's it. In order to level up on the game, you have to get better at both tasks. You get better at one task, you never get to the next level. You never get that reward. And so that's the game. I'm going to show you some data from a paper, just a bit of it, not all of it, but just to give you a taste of how we could use a video game that was custom designed in our lab as a diagnostic tool of cognitive abilities, as a neural tool to understand how the brain is functioning during these tasks, and then as a therapeutic tool to see if the closed-loop engine of the game can actually improve cognition. So what you're looking at here is a performance graph with decades of life on the x-axis. So it starts at 20-year-olds and go all the way up to 80-year-olds, so 70s. And so what we're trying to look at here is how multitasking performance changes across the lifespan. If you look at that red line, what that indicates is perfect multitasking performance. It means that you have a 0% drop when you add on the driving task compared to how you do on the sign task alone. And then all those percentages show how much your performance declines when you do two tasks versus one. Now, I'm not so sure about 20-year-olds over here in Portland, but in San Francisco, they are convinced that they are multitasking masters. It's probably true here as well. And if you ask how they'll do, they would think that they're going to get it pretty close to 0% because, they practice multitasking all day long. But what we find is that there's a 27% decrement in a 20-year-old's performance when you add on a secondary task. Now, we already know that if you look at 80-year-olds and have them multitask, there's going to be a more serious decline in their abilities. Now, I do want to point out that it's not that the individual tasks are any harder, because before they do the multitasking, we figure out their ability on the sign task and the driving task independently, and then overlay them. So everyone's doing the two tasks at their own ability level. So the road is slower, and the signs, you have a longer window to respond in the older age group. But still, when you put them together, then you get a bigger impact, and that's what we've shown through many years. But the question is, here, does this ability to function at that level maintain itself for your entire life and then just plummet in one horrible year when you're 69 years old? And that's not what happens. It plummets every horrible year. So you could see that this change is something that occurs in a declining fashion linearly across life. As a matter of fact, the data shows that the only significant decline between two adjacent decades of life are between 20-year-olds and 30-year-olds. So very fascinating what's happening in terms of the performance on multitasking. How about what's going on in the brain? So another challenge for our game design team was that they had to build a game that we could record brain activity while they play the game. We're a neuroscience lab. That's the most important thing to us, is to really understand what's going on. What are the mechanisms here? And so this game can be played both inside an MRI scanner or with high-density EEG, like you see over here. And I'm just going to show you the EEG data now from this paper. What we're looking at is a measure of activity from the front part of the brain, the prefrontal cortex, the most evolved part of our brain that's really the center of this type of cognitive control. We see a burst in activity. It's called midline frontal theta. It just means it's a low-frequency rhythm that happens in your brain, and it peaks right at the most challenging part of gameplay. You drive in the car along the road's always moving. It's like a roller coaster, and then a sign pops up. If we lock the signal in your brain right from when that sign first appears, what we find is this, if you're 20 years old. So you can see the nose pointing up, the ears are to the side, and you see that yellow over there. And that's around 2/3 the way up the power spectrum. So red is the highest activity, blue is the lowest. So we get this burst. This burst is taking place 1/3 of a second after that sign pops up. It peaks and then it declines. And what this is the engagement of the prefrontal cortex to deal with that very challenging multitasking dilemma of not having your car go off the road and still respond very accurately to the sign. Now, if we take a look at the older brain, this is what we see. So there's a peak there, right? It's not blue, but you could see that it is significantly declined. And this replicates a lot of other work. We just showed that you could do this with a video game and see that the challenge that older adults face in these type of cognitive control tasks is really related to the engagement of the prefrontal cortex and its networks with the rest of the brain. So that's the second piece of data. Then we asked the question, if we had our older adults, we actually recruited another group of healthy 60 to 80-year-olds and had them take home the game. You could see it over here being played at one of our participants' homes. They played the game for 12 hours over the course of a month. This is 1 hour a day, 3 times a week for 4 weeks. So they come in first, we study their brain, we look at a whole set of cognitive tasks, then they go home and they come back a month later. And the first thing we find is this. Their ability to multitask on the game improves dramatically, in many cases exceeding the level of 20-year-olds. But from our perspective as neuroscientists, we're really excited about this red blob over here, right? So what we see is that they're engaging their prefrontal cortex to a much higher level, many times exceeding that of 20-year-olds. And it's not just a higher level, but it happens earlier. It's a larger network of brain activity. It pretty much changes in every way to normalize all of those metrics to 20-year-old level in terms of the engagement of the prefrontal cortex. We find that even if we look 6 months later, they haven't played the game over 6 months, that there's a non-significant decline in this ability to multitask on the game. So this is very exciting. This is an example of functional plasticity of the older adult brain, showing what many of us now realize, that we retain a lot of plasticity. And when challenged in this way through this closed loop engine of constantly being pushed to the next level, we could find these types of improvements. Perhaps what's most exciting is that we were able to confirm our hypothesis. So if you look at these individuals who finished a month of gameplay and test their working memory, very, very different tasks before and after, trying to remember a face for 7 seconds, or a very boring attention span task, you find that they improve significantly, even though these skills were not directly trained by the game. So the idea was that we were able to put pressure on this system and show improvements in other cognitive abilities that share a mechanistic basis. One other piece of data that I didn't show you, but you could read in the paper, is that we had a control group. We actually had 2 control groups. A no-contact control group that just looks for practice effects. They just come in before and after. But then we had a group that played Neuroracer for a month in single task mode. So they did the driving task and the sign task, but they never did them at the same time. They showed no improvements in their ability to multitask on the game, and no improvements in these other cognitive control tasks. So what we learned here, it's not just any game. It's not even playing our game for a month. From this study, we learned that the active ingredient, using an analogy from the pharmaceutical world here, was what we call interference processing. That challenge of trying to manage both those tasks is what led to this transfer to these other abilities. Another thing that we learned is that not everyone changes the same, right? There's always individual variability. But if we look at those that show this effect the most, we find that those are the ones that show the most improvement on the attention span task, and they show the most sustained benefits on the game 6 months later. So this is how we can start to use neuroscience integrated with custom game development to understand the active ingredients and the mechanisms that take place that lead to the two things that we're really trying to accomplish, which is meaningful change, meaning transfer outside of the game, and sustainability, that the effects are not transient, they just don't go away. So we were very fortunate to have this published in this journal. This is sort of our as my friends that are musicians say, sort of like the cover of Rolling Stones for us. This was 5 years after the design of that study, year of development, 3 years of research. So it was a really exciting conclusion. And I put this cover up just to really make one particular point. You could see that nature is very generous with us with their use of a pun, the game changer, which is quite a nice one for our lab. But the challenge is that it caused me to have to message to the media all the time, even up until I think this morning, that if there's really a game changer here, it's probably not this particular game. Now, we're immensely excited about it, and I'll tell you where this game has gone since then. But if there's a game changer, and obviously only time can tell, it's the methodology. It's that you can take experts in the world of video game creation that have really mastered the skills that go into creating something that's engaging and immersive, and work closely with scientists. So you have these groups work together to build something that's customized and targeted to a deficit in a particular population, in this case older adults, and then do a careful placebo-controlled randomized study with neural measures as outcomes to understand what the mechanisms are. So if we see more of that, hopefully we will be able to make that type of impact. But if we don't, it will always be marginalized and never really fall into the world of medicine. So that hopefully is something that we'll see more of, and we're always trying to raise that methodology even to the next level in our own lab. So now let's move on and tell you about what's happened since then. There's been really two main pathways. The first was my motivation to move this out of the lab. So this was loosely a video game. I mean, it was a video game, but it's nothing that you would actually pay if you weren't being paid to pay. It's not really a fun game, right? And so the idea was that we could take high-level video game development and then take that prototype, which is really what we build, a video game prototype, build it into something that's actually real fun, right? You don't have to be paid in order to engage in it. And so the folks from LucasArts teamed up with a whole group of other friends that I had in Boston, and we helped form this company called Gazzaley Interactive Labs. So I keep my day job at the university, but I serve as an advisor for Gazzaley. And what the goal here is to use the understanding of the engine that we created for Neuroracer, but build a game that's much richer in art, music, and story. And these are critical ingredients that must be baked into the game from the very beginning, especially if you don't want to have violence in a game and you want kids to play it. So that's really what's been going on. Now, this game is not in the consumer space. So many of you are asking yourselves right now, well, I can't get Neuroracer, but can I get this game? This game is called Evo, by the way. And unfortunately, for a lot of people that feel like they want a tool like this right now, this game is not available. So while some companies have made the decision to move rapidly from the lab into the consumer space, we at Gazzaley have made a different decision. We've decided to go through full clinical testing to understand how this game works in different clinical populations. And can this actually be a type of what we think of as digital medicine? Now, all of these populations that you're seeing here have deficits in cognitive control. So it's easy to hypothesize that the engine of this game that helped older adults might have a benefit here, but we don't know that. So that's why we're doing studies. The one that's furthest along is this study here on ADD, and it actually is just now entering a full multi-site FDA approval trial to see if it can be essentially prescribable as a therapeutic device for children with ADHD. So that study started. It won't be forever for us to figure out if it worked. It'll be a year from now. If it worked, hopefully you'll see it even in clinics. If it doesn't work, we will reformulate and test again, just like is done in the pharmaceutical world, to really gain the high-level validation that the community of physicians and patients and caregivers and everyone needs in order to use something as a medicine. So that's what's going on there. As this has left the lab, it's sort of created what I think of as like an empty nest syndrome, right? We worked on this game for 5 years. The game has now left the lab. The best thing that can happen for it is that my colleagues go on and validate it at the next level, right? And we move on. And so what we've done is create a new lab called the Neuroscape Lab to take this idea of creating closed-loop systems using technology to the next level, where video games are the core, but only the beginning of what we're doing. So here's a little peek at what our lab looks like. So this is our new neuroscience building at UCSF, and this is what the Neuroscape Lab looks like. So it looks like a high-tech interactive media lab, and it is. It has the advantage of having 2 MRI scanners across the hall, a blood draw room right next to it, and access to many different clinical populations where we might do studies in here. What's going on in here? This is our experimental room. So if you were a participant in one of our studies, you would come in here and engage in different interactive media that we create in our lab. And this room is right across this wall. This is our control room. So what we do in here is we present these closed-loop interactive media games to our participants and then record pretty much everything that we can in real time. So from eye movements, body movements, autonomic responses, behavior, even brain activity. And so this is where we are trying to step into the future and both develop and validate a whole new class of tools that we could think of as medicine or also think of as types of education. Now, I just want to step through some of the technology that we're excited about. Obviously, mobile and wireless because of the great accessibility. One thing that we're learning is that it might be hard to get a doctor or a teacher into many places in this world, and I've been traveling all around it now, hearing the same challenge. But mobile devices, especially phones, are pretty much everywhere, or will be very soon. And so this is a really exciting opportunity to have underserved communities have access to this type of tools. But it's not just software delivery tools like tablets and phones. It's also other tools like this, which is a mobile EEG cap that we're right now preparing to do the first study where we record brain activity while our participants are at home playing one of our video games. So the same type of data that I showed you that was only accessible to the lab in the laboratory setting, we can now do at home. So this is one of the goals of the Neuroscape Lab, is to help develop this. There's 2 other types of technology that we spend a lot of time on. The first is virtual reality, and the second is motion capture. So there are several devices, some of which have already been released, but 3 giant ones that will be coming out this year that create these incredibly immersive real-world virtual environments. These will largely be targeted for video game use, certainly, as well as other media and communication outlets very soon. But we think that this could be used in our closed loop to create even a more powerful tool to improve cognitive abilities. And then motion capture, the idea that you can play a game with more than your eyeballs and your fingers, and what might that mean to cognition. And I'm going to give you an example of this from a lab experiment that we're doing now. One last thing I want to tell you about is a game that we call ACE. So ACE is a series of modules that we designed to be played on an iPad. And what we do here is use the adaptive closed-loop algorithms not to change your brain, but to sample how your brain is functioning. So that's the other thing that adaptive algorithms are very good at, is getting a quick estimate about how you're performing in any particular domain. It's like the type of algorithms that we use for hearing tests. And so why did we create this sort of app that has all these different modules? Is because we have this goal of not just doing experiments on the 20 people that could come down to our lab to do an MRI, but to do experiments on hundreds of thousands or millions of people. And so we need to have an outcome measure, a tool that we could use before and after training to understand if there's transfer. And so that's the goal here, to do what we call mobile randomized control trials, where we can send out our different apps into the world to see how they impact people, and then have the outcome measures also mobily distributed. We also now have a program to distribute these in classrooms around the Bay Area. That's where we're starting, to see if we could start understanding, using this as an assessment tool, to understand the cognitive abilities of students. Right now, our first program's in middle school, to see how those brain performance metrics map onto standard academic performance metrics. We still don't even fully understand the connection between those. So that's ACE. All right, let's move on to a fun part, is talking about some new games. So after the Nature paper was published and we had the Neuroscape Lab come into existence, we really have been devoting ourselves, so it's been almost a couple years now, to building new games. So I just want to take you through 4 of them and just give you a very quick view and also talk about the hypothesis of what we're trying to study with them. So the first game I want to tell you about is called BBT, also known as Body Brain Trainer. The goal of Body Brain Trainer is to challenge you in a game both physically and cognitively. So it's like physical fitness meets cognitive fitness. Now, Body Brain Trainer is unique for a couple of reasons. First of all, while you're playing the game, the cognitive challenge is scaling to your ability using the closed loops, just like I described to you, just like Neuroracer. But here, a participant here is also wearing a heart rate monitor. And this number over here, 158, is his heart rate. And so while he plays the game, his heart rate gets fed into the game engine in real time. And the game could challenge the physical demands to drive his heart rate to the level that we want. So essentially, both physically and cognitively, the game is adapting to his abilities. So before one of our participants does one of these studies, they get something known as a VO2 max, which is like the industry gold standard for figuring out your physical fitness level. And so we can really target that level so that we give someone a very personalized physical and cognitive fitness challenge. Our hypothesis here is that your outcomes, your learning, the cognitive learning, your attention abilities will be increased if you are embodied in the gameplay. If you're not just playing the game with your fingers, but you're physically embodied, you will have better learning. So we think of it as a new principle of learning, and we think we could show here in a very careful way the role of physicality in cognitive learning. So this game uses domains that focus across each of these different areas: attention, working memory, and goal management, and then each of them challenges you physically also in another way. So we're now undertaking a study on that. The next game I want to tell you about is a game called Rhythmicity. This game was inspired by my friendship with this guy right here, Mickey Hart. For those of you who are not familiar, Mickey Hart is the drummer from the Grateful Dead, and there are many musicians now working on this study. The hypothesis here is that if we can make ourselves more rhythmic, the rhythms of our brain and its timing and our anticipation abilities will also improve, and we'll see cognitive benefits. And maybe this is some of the reasons why music therapy has been around for so long in so many different cultures. And so we built a game called Rhythmicity, and what it does is it challenges you in all different aspects of rhythm. Your ability to synchronize with rhythm, syncopate, to continue to reproduce them with tempos and rudiments, complexity and speed that's constantly scaling to your ability. So it uses very sort of standard gameplay algorithms that we see in lots of rhythm games, where you sort of destroy these aliens right when they pass the points, and you're doing this rhythmically. But unlike other games like Guitar Hero and Rock Band that have music as an element, this game also has the adaptive rhythm challenge. So it's constantly pushing you to a greater rhythmic challenge with the goal of seeing, can we make you more rhythmic? And then what are the consequences on your brain? All right, the next game, Virtual Attention. I don't have artwork for this yet. This is our newest game. We're actually co-developing this with a big game company called Zynga, who's philanthropically donating their engineering efforts to help us. The goal of the game here, this is Oculus Rift, which is one of those headsets that are coming out this year. The goal of it here is not to actually teach you how to focus your attention, but to distribute your attention, the type of skill that we use when driving, and that we know declines as we get older. So this game is early, but it will be done by the end of this year. The last game I want to tell you about is called MetaTrain. So in MetaTrain, what I did was take the principles of concentrative meditation, focus on breath, awareness of where your mind is, and the return to your breath, and integrated that with our video game mechanics of feedback and adaptivity to create an iPad game that baby steps you into this process of what we would think of as self-regulating your internal distraction. The hypothesis, based on many studies of meditation, showing that it has benefits not just on stress and mood management, but also on cognition itself, to create a game to improve, again, those core cognitive control abilities that we're trying to elevate. So that's what's going on now. We have these 4 games. We have 3 other games that I haven't told you about. The top 3 are done. The bottom one, Virtual Attention, is still in development. And now, we move through a series of steps where we pilot them to see how they perform, and then we begin the deepest dive studies into understanding what these games are doing, way beyond what we did with the Nature paper. Structural MRI, functional MRI, stress testing, blood work to look at how different hormone markers and stress markers are changing over time, and of course, lots of cognitive tests. Now, it's going to be a while before we see what each of these games do independently. We've actually started already doing the MetaTrain and Body-Brain Trainer study in healthy 20-year-olds, and Rhythmicity will be starting in the next month. But the real win will not happen over the next 3 or 4 years. The real win's going to happen when we start looking at how these games interact with each other, to not step along that same pathway that we know doesn't work, of thinking of any of these as a solution in itself. So I call that neuro-CrossFit training. And I think that's where we'll really see the big impact. Now, as I said, it's going to be a while till we start looking at the interaction between these games, so I thought this was a harmless area of self-experimentation. And so last summer, I played 3 of these games, Body Brain Trainer, MetaTrain, and Rhythmicity, for 2 months, and did all the outcome measures. And I won't really reveal the results yet. We're still trying to process them. I will tell you that the Neuroman project is something that we're very excited about in the lab. So we'll have to return to that over time. I'll be doing it again this summer. And I can tell you one of the main advantages is it's very eye-opening to be a participant in a research study in your own laboratory. So I think that a lot of good will come of that in itself. The other advantage of this Neuroman project is to start even pushing us to think more about the individual. Even our lab, which is focused on individual differences, still steps along that path of thinking about populations. We need to think about the person. What does meaningful data mean to an individual? And how can we build a framework to allow someone to engage in all this training in their busy lives? So that's some of the direction that we're moving to help that goal. All right, I'm going to conclude with the most forward-thinking part of the lab. So what you just saw is really pretty much our bread and butter now and has been for years. But what we think we can do is take the effects that we're seeing from the video games. Now, the video games are our core and always will be because they create experiences that activate brain networks in a selective way. And so we get that selectivity. But we think that that's only the beginning, right? We can boost those effects higher using neural data in a very, I would say, unique approach to neuromodulation and neurofeedback. So I'm going to show you what I mean by that. But first, I want to tell you about another tool we created called the Glass Brain. If you Google this, you'll read way more about it than I'm going to tell you in the 30 seconds right now. But what you're looking at is something that we created in collaboration with folks from UCSD and a company called NVIDIA. And what you see is an MRI image from someone in our lab. We pretty much all have one of these glass brains now. And this MRI image has overlaid on top of it EEG activity. So this is electrical activity on MRI structural activity, showing in different colors the different frequencies in the brain and how areas are communicating with each other rhythmically. And this is done essentially in real time with just a 0.2 of a second delay between when it happens and when we display it. And we're doing a lot of this very sophisticated processing from artifact rejection, source localization, something called multivariate Granger causality. All of these algorithms are done very rapidly so that we can get an accurate measure of what's occurring in your brain while you play one of our games. So what do we do with this? Well, we have 2 pathways, right? This could potentially be a new diagnostic tool, right? One that we've never had before, where you could see what's happening in someone's brain while you challenge them. Now, I don't have a clinical example of this, but I have this one that's pretty fun. This is Mickey Hart, drummer from the Grateful Dead, playing a game in virtual reality. So he has an Oculus Rift on. He also has a 64-electrode EEG cap on. Now, this is at the close of a giant keynote I did for like 3,000 people that are all sitting in the audience. So what you're not seeing is that this screen goes all the way down to here. And so what's happening over Mickey's head is a view of his virtual world of the drumming game that we created that he's playing. What you're seeing here is Tim Mullen's view. He's wearing a virtual reality headset, and he's not inside Mickey's game. He's actually inside Mickey's brain. So it's sort of like neuro-nested dolls, right? Like you have Tim inside Mickey's brain and Mickey inside virtual reality. And you can imagine a future where a therapist is sitting with a patient with a virtual dashboard and flying through their brain as they challenge them in the game world to see how they're responding. So anyway, it's just an idea, sort of a fun example for now. All right, I'm going to conclude with this and tell you about why we created the glass brain for right now until we work out that potential opportunity of real-time diagnostics. And it is to ultimately close the loop. So let's pull it all together. The year is 2016. You present to a doctor, whether you're 7 or 70 years old with an attention problem, and you're likely going to wind up with one of these that's going to activate your brain in a very blunt way and cause side effects. We don't think we have to get rid of drugs. We think that they do important things to activate these neurotransmitter systems. But we think even by 2020 we could reduce the doses and then use an assessment tool like ACE to understand and to target what we want to improve in a particular person's brain, and then use a video game that's custom designed to that activates those networks, puts pressure on them through those closed-loop engine to improve it. Then the glass brain comes in. We can take EEG data that's being collected during gameplay and feed that into the game engine so that the game challenge, the adaptivity, the feedback is not just responding to performance, like accuracy and response time, it's actually responding to what's going on in your brain so that it can really target those game mechanics to the aspects of how your brain is processing information that most needs to be improved. Right? We think it's like a surgical approach to refining how your brain is functioning. We can also take that EEG data and feed it in to guide the stimulation parameters of a device like this that doesn't just record your brain, but actually stimulates your brain electrically at different frequencies. This sounds like science fiction, but I can assure you it's not. We have 2 papers that we're submitting this year, and there are many others in the literature showing that you could stimulate the brain non-invasively electrically in a safe way and help promote plasticity of those brain areas that are under the scalp. And so this is still a research topic, but the idea is that imagine someone with a traumatic brain injury that just comes back from overseas. We're trying to rehabilitate them. We assess them. We use the game to target the networks that are most challenged in their brain. We use EEG data to create a tighter closed loop, and then we stimulate their brain so that they can get maximal plasticity and recovery. And what we wind up with here is something that's targeted to the system, personalized, not just to the individual, but how they change over time, multimodal, even using drugs in a much more effective way with a lower dose, and then multiple closed loops working together. That's the vision. What we wind up with is not just this, but because we use consumer-facing products at every possible point along this development pipeline, we wind up with something that's in the real world and real time. Right now, our situation is that you come into the office, we might not see you again for months. We don't know how you're changing. We're in a very unnatural environment to sample how you're doing. But you can do this at home, both from an assessment point of view and a training point of view. And so right now, we're expanding this out to multiple different clinical populations. This is not a wish list. Someone's always going to, I know this because I give a lot of talks. Someone will say, wait, pain is not on the list. We think this could have applications across almost anything that affects cognition in the brain. This is not a wish list. These are actually the collaborations that have already started. So we're excited to see where this takes us. And remember, we're not saying that it's going to remove the underlying pathology of these diseases, but we think that it will strengthen the neural networks of the brain to at least delay the symptomatic onset of many of them. And then we have lots of interest and research projects that we've started to not just think about these as clinical tools or digital medicine, but as educational tools and wellness for people that have healthy, functioning minds. Now, I often conclude with this, but because the things that we're creating are not available yet, I find it sometimes dissatisfying to audiences. So I do want to note that there are many things that we could do right now that promote brain health that use very similar ideas to what we're developing in the lab. And it's not meant to think that this is the only solution. So I tend to think of these, what I call the 5 pillars of brain health, where we're starting to gain more and more evidence that we could help promote function in brains across our entire lifespan. So physical fitness, tons of great exercise. I already tons of great evidence about physical exercise, especially aerobic, but also resistance training, cognitive training. There's a lot of work to be done, but I think we're seeing things that give us a signal that we're going to figure it out with more research effort. Nutrition, stress management, sleep management, also very important for brain health. So I think there's a lot to do right now, but I'm pretty excited about the future and what we're going to be able to share with you over time. And with that, I'd just like to thank you for your attention.
What a wonderful talk. That was just great.
Thank you.
As you might imagine, it's generated an enormous number of questions from the audience, and we'll only have time for a few. But one of your predictions came true, which is that dozens of people in the audience would like to know whether Lumosity is headed in the same direction as you are.
I was trying to predict the questions because I've given a lot of talks, and I know the issues that people have and the questions that are generated by a talk like this. I could speak generally about the world of brain training. It is a very complicated place to be in right now, and this is not only true of the world of video games and brain training, it's true of the nutraceutical world and many other domains. And a couple of points I would like to make in general, without talking about anyone else's particular products or companies, is that not everything you do for your brain is going to be equally good. Just because the idea that our brain is plastic, which is a strong one, is well-founded, our brains also have this property known as homeostasis, meaning that it really does want to stay in a static position also. If it didn't have that, it would be very dangerous. Your brain just can't change very easily. And so we are likely going to find that not everything has the same effects. Some things improve exactly what you're training on. Some things have more transfer than others. We have a lot of work to do, both on the development side and on the validation side. And our personal design approach is to build real video games with professionals in the industry so that people engage very deeply in them. So one of our tenets of development is that if you don't immerse yourself over a continuous period of time and constantly push, the brain won't change in a meaningful way. Similar to what you probably already know from physical fitness and going to the gym. You actually have to push on the system. So we need to learn a lot in terms of the design principles that we develop with, and then we have to get better at our methods of validating so that we're really confident that the things we're creating actually work. So a lot of the things that exist in the consumer space haven't gone through either high-level development or high-level validation, or maybe one or the other. So I would say we're still in our infancy, and I just urge you to think of this when you look at what's offered right now.
So this is Portland, so there are a bunch of questions about mindfulness here. So the one I've selected asks, how does this fit in with the focus on mindfulness and the evils of multitasking that have been so popularly displayed in the press?
It's a great question. So sometimes it confuses people because it seems like I'm telling two opposite views of the same story. So I actually have a book coming out. I'm finishing it on Monday called The Distracted Mind, about the challenges of multitasking. That's what I've studied for almost 15 years now. And so we know that our brains are not optimized to deal with rapid switching and multiple sources of information, and that it causes performance decrements at worst. It causes safety issues like driving and texting, but it can impact every domain of our lives, our relationships, our workplace, school, all of that. In general, if you have to do something that requires a high level of quality, especially if it's time sensitive, you will do best to focus on it and nothing else. And so this is not meant to promote multitasking. The idea here is that we can use the aspects, and not just multitasking. You can see we have many games. We could challenge the brain in certain domains to improve its function. So you can't always do one thing at a time. We live in a complicated world with many different challenges on our interactivity. And so this part of our research is just to try to make our brains as strong as possible so that we can reach our ultimate potential. But another important message is to sculpt an environment that's most suited for how our brains function. So I don't think those are incompatible messages. In terms of mindfulness, I have great respect for many researchers and practitioners. As you know, we basically have a mindfulness video game, Metatrain, that we developed with a luminary in the mindfulness field by the name of Jack Kornfield, who works very closely with us. And so this is not to say don't do a meditation retreat, play our video game. These are not mutually exclusive. Same with physical exercise and BBT. These are tools that can help certain people that might not want to go to a meditation retreat or have trouble engaging in the gym because it's boring for them. So again, this is not a solution, but it's a solution in itself. But it's ways of taking things that are very valuable, like mindfulness practice, and finding other ways of delivering it.
Here's another Portland question, and perhaps anticipates next week's lecture. What drug comes closest to matching gaming?
I don't know. People say psychedelics are like video games, but I can't validate that. So, I think that nothing is close in the drug world to a video game, because with the video games, we create this very powerful experience that we curate and control. And so through the design that takes us years, we create this, really a selective way of activating your brain. And I know that we have no drug that does that right now. It doesn't mean that we never will, but we just haven't been able to target them at that level. I think that it's going to be really interesting to think about drugs combined with this type of interactivity and this type of experience generation to hopefully get even more out of them with less side effects. So that's my answer to that one.
So here is quite an interesting question, I think. Could the kinds of video games that you are designing be used to train very difficult professions such as neurosurgery in the future?
Undoubtedly. I just gave you a sort of fragment of this field, right? I largely focused on medicine. I gave some shout outs to education. I could have given this lecture and not mentioned medicine at all. I could have just totally did it from the perspective of developing minds. It can also be done from the perspective of people that are healthy, just want to optimize themselves, where the mindfulness world is often, firmly planted. But there's also all types of high-level training of people that need to optimize their performance in very critical situations. Sports, military, surgeons. There's going to be great potential for games to benefit all of those individuals. I really do think that's true.
So some of the techniques that you are experimenting with involve a kind of mind reading or awareness of the machine of what is going on. And that relates to this next question, which is, do you agree with concerns about artificial intelligence that have been expressed by Hawking's, Gate, and others?
Yeah, so I think the world of AI, for those of you that have not been following a lot of the high-level critics of it, is certainly something that deserves a lot of attention and real responsibility in terms of its development. Our work with machine learning algorithms, to use a more specific approach, which is the type of adaptive engines that sit in our games. They're not really AI at this level. They could be made to be more intelligent in some ways. Not the same type of intelligence that we're talking about here, but a richer way of receiving information and creating environments. My idea about AI is to use it as a tool to improve us. And not as a way of replacing us. And so we're always focused on bringing all of this technology to human betterment, improving our quality of lives. So it's not an answer to it, but I think as long as we keep humans front and center, that it's really about us, that's why we're creating these things, I think we'll wind up with a better outcome.
There were several questions related to concerns that mainly parents have about their kids playing video games and spending enormous amounts of time doing it. Are there games you think that are deleterious?
So this is a very complicated research area. There's two main aspects of games that come under the highest scrutiny in terms of the negative effects, and that would be the violent content, as well as the potentially addictive nature of them. I don't research either of those things, so I don't have a strong opinion. I can tell you, if you look at the data, and I've looked at it for a long time, there are two opposing camps on most of these things. So the data is not completely clear on either of them. And a lot of it is due to the problem that so many people play video games. It's really hard to do these studies in a controlled way. I could tell you that when we think about those things in our world, right, if we're going to build a new type of medicine here, if that's really going to happen, I don't know for sure it's going to happen, but we're really confident that we're heading along that pathway, it's responsible of us to consider those side effects. And as a matter of fact, put those side effects out there when we go for things like FDA approval, which we have. So the first thing we do is we don't have violent content in our games. We think that you could create engagement, as I said, through art, music, and story. It's expensive to bring those things in. You need experts, and it's hard to create fun games without using tools like violence, but it's possible. The other thing that we think about a lot is in terms of addictiveness and how much use. Now, this is not true of just games, but there are many, many things that are good for you that are not great for you in excess, right? The list is long. So video games is just another one in that list. If you play video games all the time and never engage with other people, That's not a great thing. I mean, it doesn't take a study to figure that out. So this is certainly not what we want. We don't want to put these things out and have them be a replacement of other valuable real-world interactions. In our particular study right now of what we're doing to control that is that when our participants play EVO in the study, they play for half an hour and then it won't play anymore. They have to wait till the next day in order to re-engage in the game. And so unlike drugs, we get the opportunity to both monitor compliance and to control the delivery in a very careful way because it's software. So we could control how much you play our games in a very fine-tuned way just by building it into the game. So that's one way that we think about, and it will be a very interesting topic over the years, to deliver it in a very controlled fashion.
So some questions from the audience concerned the treatment of various psychiatric disorders, which you alluded to in the last part of your talk. One person indicated that they had played games and it had really improved their social anxiety disorder because of the ability of the game to enable them to interact with characters. Do you have any comment on this?
Yeah, that's another vast area. Video games are a very, very broad genre. I mean, it's literally like saying sports or food or drugs. There are many, many, many different, very, very different types of games. We're talking about one type of high-action interactive game that we develop in our labs, but there are social games that take place over long periods of time. There are games that have more poorly defined goals, like sandbox games like Minecraft, and we don't understand that they will probably have different positive and even potential negative effects compared to each other, just like drugs do. One very exciting part about games, especially recent games, is their social aspects. A lot of people think that games are isolated. That's not true. There are many games where even if you're not seeing another person, which is a potential negative, but they do have high degrees of interactivity, not just with game characters, but with actual people all around the world. And we expect that this will change even more so with virtual reality. So I think there's really exciting potential for social interactivity in games. I know there's lots of interesting games for autism for this very reason. So, you know, it's really a very open-ended question, but I think the social human-human interactivity in the game world is going to be very powerful.
So there's a certain amount of impatience in the audience that your games are not yet available, and this is encapsulated
So I finished with that last slide. That didn't help.
This is encapsulated in one question, which is, do you have a game that you would recommend for an 80-year-old?
80-year-old. The problem with games is that traditionally, they were not built for older adults. Everyone knows that. That is just the reality. They were not even built for women. They were built for young boys, and that's really the population that likes violent video games. That has changed dramatically, right? Now it's 50-50 male-female that play video games around the world. The average age of a game is pretty much 40 years old now. And if you look at the numbers of seniors that play games, the numbers are increasing, especially with grandparents playing with grandkids, which is a rising phenomena that's quite interesting. So the game world is much more mature than it was even 5 years ago and increasing all the time in that way. But the problem often is that they are still not targeting the older audience as well as they could have. It's actually a problem that I talk about all the time. It could be done so much better. It depends. So I'd say the answer depends on whether or not you have game systems in your home. If you have grandkids, then you might very well have them there. So there are games that really are incredibly creative, artistic, journeys that are appealing to different audiences. There's a game called Journey I like a lot. Flow is a great game. There's a game called Portal 2, which is my favorite game of all. It's a spatial game. I don't know. I don't have a great answer for that, but I could tell you that you will see more and more games that are really entertainment purposes, but they will be appealing to different audiences because I think we're just beginning to open our eyes to this potential.
And a related question, do you need volunteers for your work?
Great question. We always need volunteers. The challenge is that most of our studies are done at the university in San Francisco because we do MRI scan. You know, we're a neuroscience lab, so even though we build all these, we do these deep dives in the lab where you really have to be local. But that will change this year. if we're lucky. There's lots of technological work that we're doing to build a whole server side and back end. We're really trying to get our games, especially the mobile games, distributed broadly. We're talking with Apple and other big companies about the potential to do this. These are tough problems for a laboratory, but we do hope that we will be enrolling participants all over the world even in the next year or two. If you go on our lab website, if you search my last name, you'll find our lab website very easily. We have a newsletter that we actually will do a better job of maintaining, and you can read about our studies there. I have other talks I've given, all of our research articles, so it's a good resource if you're interested in this.
The Twitterverse has been active, and I believe we have a few questions from that sphere. Are there any differences in brain images when comparing solo players versus team clan players?
That's a great question. It goes back to the social one that I told you about. I don't know if there's an answer to that yet. This is a really early field, and this is a pretty sophisticated question. We haven't done any. All our games are solo games right now, and not because we don't like interactivity. It's because it's already hard enough for a laboratory to build video games with one player, and it does get more complicated from a programming point of view. So I would say that the jury's out on that right now.
I think we have another question. Here we go. What was your favorite game as a kid?
Oh, boy. I never get asked that one. I get asked what my favorite game now is, and I told you Portal 2 would be my favorite. I'd say as a kid, my favorite game, the only game that I ever finished that no one actually knew was possible to finish was Asteroids. I sort of was pretty, everyone like Asteroids? Simple game, great game. I'd say Asteroids.
Well, I played that one too. Do we have one more from the Twitterverse? What about there's no such thing as multitasking theory? Does trying to do so just keep us from doing either thing well?
Yeah, so we talked about this already. As I said, this was like my main research focus. It's what actually got me into the world of video game training. Multitasking is a behavior, right? It's something that you try to do. I think it's a fair word because sometimes you're like, I'm going to do those two things right now. Thus, you're multitasking. But the reality is, and why people say there's no such thing, is because, and we've done this in our own lab, we have lots of data on this, when you actually do the multitasking behavior, what happens in your brain is really switching between networks. If both the tasks are attentionally demanding. So if somehow you think that maybe chewing gum is a task, which it probably might not be, you can do those two things at the same time without switching because one is offloaded to very reflexive systems. But if both tasks demand attention, you will tend to switch between them. It could be very rapidly and completely unknown to you. With each of those switches, whether or not you intended to switch, or you tried to actually simultaneous process, with each switch, there's what we call a cost. That's why you saw that other sentence that said cost of multitasking. I showed you an example of multitasking in 20-year-olds and how much they suffered. When you move between networks, there's a loss of speed, of efficiency, and so, as I mentioned, if you really have something that's demanding, I think it's pretty clear that moving and returning to it will result in some performance decrement.
Great. Dr. Gazzaley, it's been a wonderful and fascinating presentation. We'd like to thank you.
Thank you. Fun.